A very warm welcome to the Science Technical Division's fourth online lecture for 2023. Just a couple of things to note for the lecture. Teams webinar creates an attendance register at the end of the meeting, which will be used for CPD purposes. Hence, there's no need to leave your details in the comments section. The lecture is being recorded. If you choose to stay online for the lecture, your consent to the lecture being recorded is implied. For the Q&A portion at the end, please click on the Q&A icon in Teams and post your question there. So without further delay, let's get started with the lecture. Karl Terzaghi of Arab Australia will be presenting his lecture titled Design Philosophies and Geotechnics, Thoughts and Practices from Karl Terzaghi. Segei was born in 1963 in Eugene, Oregon. He completed most of his schooling in New Zealand, barring 1 year in Austria. He graduated with his honours degree from the University of Canterbury in 1986. He started working in Auckland at a small local firm called Murray North, working on a wide range of engineering projects throughout New Zealand, the South Pacific, and Singapore. This proved to be ideal training for a geotechnical engineer, given the wide range of geotechnical materials and complex problems he encountered. Murray North was acquired by Woodward Clyde in 1993. This expanded their range of operations to Western Australia and Western USA. He moved to Sinclair Knight Mertz in 2000, seeking wider opportunities. This added Australia to his sphere of operations and resulted in him moving to Australia in 2005, and he ended up at Arab in 2009. He had a short spell in Los Angeles as well, between 2017 and 2019, but ultimately found his way back to Sydney, where he's currently based and working on projects worldwide. With the introduction done, Sergey, over to you. You can take control and share your presentation.
Right, thank you. Just worth noting, working internationally, I'm currently in Kuala Lumpur rather than Sydney. Just going to prove the point. Right, as mentioned before, I'm just going to talk about some of the design philosophies in geotechnics, from some of the thoughts from Karl Terzaghi. And this really came from discussions with Sukumar and Harry about the ISSMG time fault, and developing thoughts about what Karl Terzaghi might have thought today, what he thought at the time, and based on various recollections I've had, various discussions I've had with people and who both knew Karl, worked with Karl, and of course family. And of course it's very timely because from a geotechnical point of view, it's 100 years of many critical pieces of work that Karl has worked on. Consolidation theory, which developed in Istanbul between sort of like 1916 through to about 1920. Publication of Erdbaumechanik in 1925. While he was in Istanbul, he worked on earth pressure theory, validating the concepts around earth pressure theory. Actually prior to that and subsequent, he worked on things like filter theory, a lot of the road stuff, the CBR concepts, all came from Karl around about 100 years ago. So very, very timely. Also thinking we're getting very close to Karl's birthday. He would have been born nearly 140 years ago. So how I'm going to do things is I've collected a series of quotes or extracts from Karl's talks, papers, and other sources, look through why it was important at the time, why it's important today, maybe some things to think about. I'm just going to also then veer at the end about consolidation theory, where it was, how it was developed, where it needs to go today, and then maybe some thoughts about how the profession might move in the future. So starting off with ethics. And this quote comes from a paper I'll talk about later. Engineering is a noble sport which calls for good sportsmanship. Occasional blundering is part of the game. Let it be your ambition to be the first one to discover and announce your blunders. If somebody else gets ahead, take it with a smile, thank him for his interest. And if you begin to feel tempted to deny your blunders in face of reasonable evidence, you've ceased to be a good sport. You're already a crank or a grouch. I find this particular quote kind of interesting, partly because of his background. He was raised in a military family. He was part of the Austro-Hungarian Empire, which was not particularly renowned for recognizing mistakes, and had become a little bit stultified in its behavior. However, it was also a recognition that he was at the forefront of a new science, trying to turn what we now know as soil mechanics into a science rather than a black art. And, there are a lot of things, a lot of concepts that were very, very challenging. They're still very challenging today, and we'll discuss some of those things later. And the thing we have to recognize is soils isn't a ideal material. It's a natural material with wide variability, often in short distances. So you need to recognize the issues and recognize that our investigations are not don't really pick up that variability. The worst habit you can possibly acquire is to be uncritical towards your own concepts and at the same time skeptical towards those of others. Once you are at that state, you're in the grip of senility, regardless of your age. I think this is really important. We need to keep challenging our designs, our thoughts, our concepts that we're behaving with. And, continually ask ourselves, is the code, is the concept that we're looking at, is that appropriate for the circumstances? Very few people are either so dumb or so ignorant they could not learn anything from them. And, everyone has a role to play, and many key observations can come from non-professional people. And it's really important to take all those observations into account. And, as I've already discussed, the strict military upbringing. Now, there's a little bit of interest there because while he was born in Prague and he spent his first 10 years in Prague, his father died at a comparatively young age. And he moved back to Graz, where his mother was from, and to be with her father. And so it's Karl's grandfather who brought Karl up effectively. And that gave him a lot of latitudes. And at university, he was always let's just say bending the rules quite considerably. But he got through that, and we'll talk about some of those issues later on. But he finished his engineering degree and moved on into doing other things. But he found a lot of issues, and being on a construction site where the I-beams were patently too small. He could push them, move them, just by leaning on them when it's supposed to be part of a multi-story building. And, this led to all sorts of things and really, started forming some of his thoughts and his behaviors. The outcomes during the First World War. He was a test commander or he's commander for a test squadron. And the issues there were very much reflecting the sorts of thoughts that I've just discussed. It was also recognizing it was at the start of a new field, and we didn't have answers. We didn't even know what the questions were that we had to ask. So it was a lot of observations, and recognizing that these observations may not always be universal. And of course, it's still good advice, but the putting it in application is often difficult given the commercial and practical realities working today. There's a very big difference between what he could do in the 30s, 40s, and 50s compared to what we have today. And I often point out, when he was working on the Chicago liner tunnels, which led to a lot of very valuable concepts, like the observational approach. It's really where they started discovering the realities about undrained strengths as versus drained strengths. They had no problem with buildings settling 450 millimeters or 18 inches, if you prefer. They had an army of people going around jacking up the buildings, refilling, then releveling, and doing whatever else that needed to be done to make good. Today, of course, if you even suggest the building is going to move 25 millimeters, you're going to have an army of lawyers baying for your blood, which makes it very difficult to actually practice some of those thoughts and ethics and really look and learn and challenge the realities. Equally, for all the advances that we have, there's still a lot more to learn, to discover, to explore in our field of geotechnical engineering or geomechanics, if you prefer. Moving on to analysis. Mathematicians are useful animals who should be kept in a golden cage and fed problems judiciously. And, this really reflects the huge gap between analysis, mathematics, and what's really pragmatic and what really we can do on the ground as a practical problem. And there's multiple aspects to this. Just some background on some of those things. I've mentioned before, he was very much a wild character at TU Graz. Got involved in all sorts of scraps and illicit or near illicit activities. One of them being belonging to what was called a dueling club, where they used these barbaric swords that were more about scratching each other, leaving marks on people's faces or hands rather than killing someone. But even so, it was very much on the edge. While I was at Istanbul developing consolidation theory, he was able to prove and practice the concepts of the consolidation theory on one project where people were going to use piles, floating piles, which clearly wasn't going to work when you started applying the concepts from consolidation theory. But equally, applying the theory, when it was called in to the same client looking at a settling jetty, applying the concept of consolidation theory, he learned that the issues weren't that the clays that the jetty was founded on was consolidating. It was that the piles had rotted away or had been eaten away by teredos. So it was really learning the lessons about, yes, you've got theory, but you also have to apply it pragmatically. Later on, there was the Fellinger affair. And this is at a time when Karl had moved to Vienna and was teaching at the TU Vienna or TU Wien. And Professor Fellunger was Karl's counterpart in continuum mechanics. However, he was applying the straight mathematical theories of continuum mechanics, whereas Karl was applying them from a practical viewpoint. And really, Professor Fellunger had little practical understanding of those issues and attacked Karl's theories and thoughts and was trying to demonstrate how unrealistic and how non-physical his theories were. Now, of course, from a modern day point of view, they were both correct. It really depended on the viewpoint. However, because they could not overcome their differences and misapplication of some of those concepts I've talked about before, it ended up that Professor Fellunger was bound against by the community, and he went and committed suicide, which was really unfortunate because it was a very much a missed opportunity for soil mechanics, because if Karl and Professor Fellunger could work together, they would have made many very serious advances in consolidation theory in many other areas as well. And of course, we had the Chicago subways, where there were a very complex analyses for the time on the liners, but because they had no real understanding of how soils behaved, what were the real loads, there was actually no benefit, and the liners were in reality completely misdesigned. But we had no better way of doing things at the time. But it did leave a lasting impression with Karl about the misuse of mathematics. Now, of course, we could ask today, are we falling into the same trap, with over-reliance on finite element or other numerical methods? Do we actually understand the sensitivity of whatever analysis we're doing to the inputs? But even before that, do we understand the questions being asked? There's so often I look at an analysis and a design, and the question is, are people understanding what are they analyzing, but what does success smell like? People will go and, for example, design a retaining wall without thinking about what services are behind. What does the client really need? What does he want? Why is he asking for this retaining wall? What are the other constraints on the site? Which then leads to an incorrect design and inappropriate analysis. And this, we have to keep asking ourselves: are we doing the appropriate analysis, or should we maybe be the mathematician in the cage if we just keep analyzing without asking what's the practicality of the analysis we're doing? And I put this model in here because this really illustrates to me one of the issues. Is you can see the red zone on the left-hand side there. The model that was being used was a linear elastic model, which did not develop any active zone. And if I was to take that model correctly, I would end up having to completely redesign the vent shaft, because it would have been broken in two by the movements induced by the excavation that you can see on the right-hand side. And that really is reflecting the issues around, do we understand the inputs and what the implications of those inputs are? A lot of these thoughts are captured in this paper here, Consultants, Clients, and Contractors. written in 1958. And it's sort of a synopsis of a lot of his thoughts, the reasons why he is what he is, some of the issues that he's dealt with. I think it's something that all engineers or all geotechnical engineers should read, just to have a background and understanding of how our profession has developed. The problem is, Ralph Peck wrote a very similar piece in the late 60s. John Dunnicliffe wrote something similar in the 90s. It was quite coincidentally, one of my senior colleagues, John Davies, is writing a very similar piece for a conference right now in Southeast Asia. And they all share very, very much similarities around understanding the clients, understanding contractors, understanding the role of the consultant, making sure that we cut our cloth to suit, and understanding the limitations of the data that we collect, the methods that we collect. It's all very much part and parcel of the profession we are in, and we need to keep it in the back of our mind. One of my pet peeves is geology. You need an ounce of geology for every pound of soil mechanics. I would say that you need more like 5 tons of geology for every pound of soil mechanics, because if we don't understand the geology, how can we make sense of what the geotechnical properties and behavior of the site's going to be? There's the notes in so many places where Karl remained on site for a few extra days to complete observations of local geology, just to make sure he understood what was going on site, to make sure that he understood what was happening, and also to see what were the behaviors of the materials on site. I think it's also not often recognized that Ruth, his wife, my grandmother, was also an accomplished geologist in her own right, and was able to be a sounding board for Karl in many of his projects, and making sure he understood the geology and the implications of the geology for the project. And he really recognized that importance of understanding the geology and what it meant for the project. And you can see one of the sketches there from steel support and rock tunnels is understanding the impact of geology on the project and making sure that you took that into account. That was revolutionary back then, and I often feel it still is. The number of times that I read a report which has no understanding of what the geologic setting is and what it means for the project. If there is reference to the geology, it'll be just quoting the local geologic map, and the site is located on these these formations, without understanding or demonstrating any understanding of what that means for the project. And I've taken a sketch from one of the projects that I worked in the past, where people didn't understand. They just thought of it as, oh, it's a floodplain, we've got some alluvium, and we're on to rock. And it turned out that a lot of the floodplain was actually on Pleistocene deposits. They behave very differently to the alluvium. We had riverborne freshwater deposits. We had the same materials deposited in an estuarine environment, which behaved totally differently. We had gravels, which people didn't understand how they were deposited, why they were there, what it meant. And quite honestly, this was for developing a bridge across the floodplain and river that led to huge misunderstandings and a very expensive bridge that by understanding the geology, they could have saved a lot of money and a lot of other problems that developed down the line. So yes, understanding the geology is very, very important. And understanding the derivation of the materials on your project site is key to coming up with a cost-effective design and a durable design. And of course, that's becoming a more and more important and more to the fore. I'm going to move a little bit now onto consolidation and talk about some of the issues that are still around, still to the forefront. And consolidation as originally developed by Karl was representing the understanding of materials at the time. So it was using a linear elastic porous medium. Linear elastic meant that it was reversible. There are very certain behaviors associated with all of that. And that, of course, meant that he could develop a set of differential equations that were then easily solvable because they were directly comparable to heat conduction problems or heat diffusion problems, and there are very well-known published solutions for that. So that was a blessing in disguise for him, and it was one of the few areas where a lot of the terms, the variations in terms, the non-linearities cancel each other out. And of course, that is the problem, is soils are plastic, they're irreversible. Once they deform, they're definitely not elastic, they're non-linear, both in terms of stress and strain, and they undergo shear. And all of those have implications which very often are not reflected in any of our calculations, and certainly not in our methodologies, unless, of course, you go to one of the more advanced methods and solve problems through an appropriate formulation and finite element. There's also a lot of issues around interpretation, and on the right-hand side, I show the same sets of odometer tests represented in three different ways. The top one is our standard E log P plot. The second one is natural scale. And the bottom one is where we plot the odometer stiffness against confining pressure. And you can see there's very, very different behaviors that are reflected in each of the plots, yet they are the same material. Which is really challenging, and we need to look at ways of doing better. And Karl did recognize that, but there weren't the developments in his time to look at that. And I keep coming back to the plasticity because I see so often people just rely on 1D analysis for the consolidation without thinking is what's happening in the soil. And what's happening elsewhere. We have these tools that Karl didn't have. We should be using them. And one of the consequences of not thinking about these things, if we're looking at building an embankment, we increase the shear first. If we look at a normally consolidated soil, we build an embankment, we increase the shear. We start off, and that shear is going to actually want to increase the yield on envelope and induce additional consolidation in its own right. And that's even before we have any volumetric changes due to the compression of building the embankment. Why is that important? Well, if you don't take it into account, you can all of a sudden have compression and contraction of the soils, even though it was never overloaded, and you have problems develop. And this was a preloading design that I reviewed many years ago now, which really alerted me to the problem. And the little tiny embankment that was what was being built actually failed just before opening. And it's asked, why did it fail? Well, it had that huge surcharge on it, and all the pore pressures were dissipated, so it should have been completely stable. Well, the issue was all the shearing that was induced because of that toe induced its own consolidation, which happened over time and basically brought the embankment down with it. So it's something that we need to look at and learn, and it's one of those things about going back to the mathematicians. The mathematics is one thing, but understanding what the mathematics is telling you and being able to apply that in the field is something entirely different. And that's part of the reason I'm bringing this out is really reflecting that, yeah, it's good to understand the fundamentals. It's an essential part of being able to function, is understanding those fundamentals, but you also need to be able to apply it in a practical sense. And, this means, we have a lot of tools now that Karl didn't have back then. A lot of these tools were developed, evolved from a lot of the concepts that Karl developed, and we'd be foolish to ignore them because they enable us to do better designs. Bearing in mind that actually a lot of our testing techniques haven't developed much further than what he had back then. And so there's a lot of reliance on the pragmatic, on the field observation, on being able to go out on site and see and make sure that we are doing the right things, making sure our designs are sufficiently robust to deal with the variations that we are likely to encounter. And that understanding the geologic history, the site history, is going to help us develop further. And looking at how these things are going and how they're developing, can we prepare ourselves for the future? Looking at the things that has happened, has developed, and some of the things, think about how speed of communications have developed. For my grandfather, it was telegram. That's how you communicated long distance. Short, very short, abbreviated sentences. It got evolved into telex. When I started, telex was still around, which then evolved in fax. But the point is, Telegram, Karl moved from continent to continent on ship, 9 days across the Atlantic. I think most of us would think, great, 9 days in a ship, no one to talk to, I could get all this work done, as well as enjoying whatever facilities that the ship had. Whereas, when we moved to fax, clients would get their fax and look at it and send a reply the next day. And that's including the entire report. Even and then mail. Take a few days for a report to get off and a few days for a response to come back. Then we have email and instant messenger. I could add, video conferences to the immediate response. And I'm sure things will move on from that in one way or another. Of course, I don't have horseback and at the start. That kind of predates the characters in this discussion. But the point is do we have a framework to cope with the speed at which things are happening, the speed at which clients are demanding things? And we have things like AI coming up that's going to be challenging the way that we work. And there are real issues with all of this, because a lot of these tools don't have the innate quality checking, the sense checking as does the data make sense. They haven't been out to site. And it's something, I keep coming back to, is there's this huge rush to automate everything through scripting, through AI, through machine learning. What happens when it all falls over? Your slope falls down because people missed the clay seam. At least if you're on site, you might have a chance to see the clay seam and take appropriate remedial measures. But how's an AI going to do that? Especially if it doesn't understand the geologic context. Have you made sure you've stepped back and thought about the problem? May only be a few minutes just to look and consider what are the issues that we need to be considering. What does the client really want? What are the stakeholders that we need to be thinking about? Taking the sanity checking. There's a lot of things like that, and very simply means that for us as geotechnical engineers, I think have a very secure future, but only if we take a lot of these concepts to heart and make sure that we keep challenging ourselves to make sure we understand the site history, the geology, and evolve the material thinking. What are the things that we don't know, that we should know about the materials that we are dealing with on a regular basis, because we can do that better than any AI or ML type process at this point of view. Yes, we have to also acknowledge that a lot of our designs, a lot of our routine work may well be done better and more effectively by these modern tools, but that should give us more time to make sure that the underlying design and the underlying philosophies are correct. So it's really adapting ourselves to use those sorts of techniques. So I think I've spent enough time talking, and I'll open the floor for questions.
Thank you, Segei. Yeah, if there are any questions, please use the Q&A icon or just put your question in the chat. Let's give a couple of minutes. It looks like you might be off the hook.
Oh dear. It's very, very unusual.
Okay, well, yeah, we've got one
No,
from
so
Charles
yep.
in the chat. Shall I read it to you, or
Yep.
you've got it?
Yeah, I've got it. So you mentioned lab testing lagging. Do you think they still have a place in design? Site investigations, lab testing still have very much a place in design, but one needs to consider what the lab test is telling you. What is the applicability to the design? Now, and for me, one of the best tools that we have that wasn't available to Karl is our site shear wave and P wave measurements, because especially the shear wave gives a direct measurement of your G naught, your small strain stiffness, which with an appropriate site-based correlation is probably much more applicable than, for example, a stiffness derived from a traxial test or a odometer test. However, if you've got your site G naught, you've got your traxial or odometer stiffnesses, and even better with your traxial, you've done a bender test, you can start developing how the concept of how the stiffness changes, both with confining pressure, but also with shear strain. And you can use that to develop a much more effective design and understand whether the material is really as sensitive as what people might claim it is, where the sensitivities are, and give you ways around that. So yes, there is, and I think there's a lot of things that we can be doing in lab testing to make the results a lot more sensible.
Thanks, Sergey. I think, here's another one.
If you were a fresh geotechnical graduate, would you start at Karl's handbooks to understand these concepts, or what resources would you be using, geologic and geotechnical concepts? It's an interesting question. Certainly, I really like the first and second editions of engineering principles and soil mechanics. A lot of very practical advice in the different chapters, which unfortunately seems to have gotten lost in the third edition. I think there's a lot of I think there's actually a missing gap on the resources that are available to help illustrate the geologic and geotechnical concepts, to be honest. So I'm not sure I have any good recommendations at the moment for a graduate engineer. And it's something that the graduates I deal with do raise on a regular basis. So the question, which part of the embankment problem actually caused the failure to initiate? It was actually the toe of the embankment of the preload, or sorry, surcharge that generated the compression. So there were no wick drains underneath that toe. So that area never consolidated as quickly as the other areas. So we had the double whammy of the soil wanting to consolidate from the weight of the toe on top, but also the fact that there were a lot of additional shearing going on in that area. And then when they removed the toe, everyone thought it was all going to be okay because removing the toe would induce a suction. But they didn't compensate for the fact that there's also the additional excess pore pressures due to the shearing. And as that settled out, that actually dropped and removed support from the toe of the embankment. I hope that answers your question.
We've got 3 more questions in the Q&A section.
Okay. So I see the question from Peter Davies, some thoughts on satellite imaging. Absolutely. INSAR, to me, is one of the great tools that we don't make enough use of. It's not, you're talking about a tailing storage facility here. I'm looking at it right now for monitoring construction of a metro line. There's some big embankments that might be moving. We think the INSAR type imaging might give us a better understanding of the shrink swell behavior of settlements of creep than any other method. And then there's a lot of other applications, and point clouds as well. I can't understand. Road authorities, rail authorities should just do a point cloud image of every cutting, every embankment, every 6 months, and then use that point cloud to see what's moving. Where are the problems? So yes, definitely. Very good point. Thank you. You did touch on the topic of AI. To what extent do you think AI will be used in design? And would it be to the point of placing a risk on job security for designers? I think there's a real likelihood that a smart team of engineers will be using machine learning, AI techniques to basically do routine design a lot faster. Much more in conformance with the codes and standards and particular recommendations, which obviously puts a a risk on the designers who rely on that sort of work, or puts their jobs at risk. Equally, I don't see it's likely that AI, at least in its current iterations, are going to pick up when things are unusual, when they require something outside of the ordinary. So that means that there's going to be increased job security for the engineers who can pick up those sorts of pieces, who can identify and come up with solutions. So it's a bit of a double-edged sword there, and really transfer the skills. So if you've got specialist skills and those sorts of things, I think you're pretty well secure. If you're in a lot of routine design, you probably need to be looking at how you can be using the AI and machine learning, because you're going to need it to stay in business. Transfer of skills into a new area. Okay, we also believe that automation is miles away from replacing physical inspection and interpretation. Saying that, where do you envisage the future of geotechnical engineering? Have we peaked as a discipline? What's next? Foundation designs for Mars? Well, I think foundation designs for Mars or on the moon is going to be one challenge for the future, but we certainly haven't peaked as a discipline. I think we've barely started as a discipline. I think there's a lot more that needs to be found out, that needs to be evolved, that needs to be developed. There are lots of foundation techniques that we could be doing a lot better. Economical design, new techniques of installing things. I'm involved in an interesting discussion in Sydney right now where people are looking at a different way of installing a pile into the sandstone bedrock, and what are the consequences of that for tension capacity in particular. The basic idea of having teeth on your casing and using that to bore in, it seems to me quite sensible. But there's a lot of thoughts, a lot of work that needs to go in to prove it and to develop it even further. Pile design is a bugbear for me. I think it's only 20% of where it should be and could be in a range of materials. And the same sorts of things go in a lot of other areas as well. Okay, point cloud. So a lot of modern survey equipment will basically use laser imaging, and with a laser beam to take a lot of point measurements on, say, a rock face or building. And so what they generate is this 3D coordinates of the image. If you look at it, it looks like a whole pile of points in a cloud-like form, but you can then, through various software, interpret it to get very good coordinates of your building. You can pick out every joint, and if it's a masonry block, if it's a rock face, you can pick up all of your defects and then start generating your defect mapping for joint analysis, wedge analysis, and stuff like that. So it's one of the big innovations in the survey space, and something that I think we could be doing much better at and at using it in our day-to-day work.
Thank you, Segei. I think that's probably all of it. So yeah, I think we can bring this lecture to an end then. I'd just like to thank you for taking the time to prepare and be here today and to present to us. I think this was a very interesting presentation. Any parting shots from your side?
No, I just hope that it's opened a window into Karl's past and how we can maybe apply some of his learnings to our environment today. And thank you for all the questions. Very useful and very considered.
Thank you very much, Segei. Okay, so that brings our lecture to an end. We still have one more evening lecture planned for 2023, so please keep an eye out for the dates and times in the GeoDev newsletter. Till next time, thank you very much. Goodbye.